Inverse functions. An inverse function is a function that's formed whenever you switch the x and the y. Now, I mean literally. You're going to swap places, x's and y's, in the problem. So, given the table for this function, let's switch the x and y for each point. When you do this graphically, it's actually quite simple. You're literally going to switch the x and the y spot as an ordered pair. So, for example, this first ordered pair from the table, negative 1, 2, is located here at negative 1 on the x and 2 on the y. When you find an inverse, you literally switch the x and the y spots. So the 2 becomes the x coordinate and the negative 1 becomes the y coordinate. Now, I'm actually going to do this in a different color, which would have been smarter from the beginning, but whatever. So 2, negative 1 is right here. I'm going to even write over that. 2, negative 1. So now we're going to switch each one of these. We'll start with graphing them as they are in the original table. So 0, 4 is located here. 1, 6 really awesome dot right there. 2, 8. It just so happens that each of these dots starts to form a line. It has a consistent slope, a rise of 2 and a run of 1. It has a y-intercept, in this case, of positive 4. If we were to connect these dots, it would definitely be linear. I'm going to go ahead and do that. So forgive my terrible graphing, but there it is. Now, its inverse, the inverse of this linear function, literally switch the x and the y. So 0, 4 now becomes 4, 0. 1, 6 becomes 6, 1. And 2, 8 becomes 8, 2. These 4 points coincidentally also make a line. Their slope is different though. Their slope is rise 1, run 2, so a slope of 1/2. And if you were to continue this line in both directions, you would see that its y-intercept would be at negative 2. Now, I'm going to keep this line going. We actually can see where the graphs will intersect. I'm going to draw this line as well, as best as I can. So I want you to notice something here. I'm going to borrow one other color, purple. When you look at these two lines, they are reflections of each other. We've swapped their x and the y. Now the question is what are they reflections? Where are they reflections? And what is that over? That's a really weird way to say that. Here's what I want you to discover. Every time you do an inverse function, the graph of the original and the graph of the inverse will be reflections of each other over the linear parent function. So here's the linear parent function, y equals x. An inverse is always a reflection of its original function over that axis, over y equals x, over that linear parent function. It doesn't mean your graphs have to be lines, it just means it's going to reflect over that parent function line. Whatever it looks like, doesn't matter. So, back to what we're doing. How you denote that an inverse function f of x is called, so the inverse of the function f of x has a certain notation, and that notation is f to the negative 1 of x. That cute little negative 1 as an exponent is the mathematical way to say inverse. So if you ever have f to the negative 1 of anything, anyone reading it that has math knowledge will understand that you're talking about the inverse of whatever f of x, the original function, is. So that's graphically how inverses are represented and found. You can also do this in an equation, quite simply. So how do you find the inverse of a function? Super easy. Step 1, literally switch the x and the y. So we're going to take f of x equals 3x minus 2. Another linear function. Slope is 3, y-intercept is negative 2. How do we find the inverse of that function, algebraically speaking? So step 1, switch the x and the y. And I mean literally switch places. Now you have to remember something. You have to remember that f of x is a fancy way of saying y. So your original function sure does have an x and a y in it. When we switch x and y, we literally write the x in the y spot and the y in the x spot. So I want you to notice that the 3 and the negative 2, they didn't change spots. It was just the x and the y that moves. So step 2 of this process is solving for y. If we're going to graph anything, eventually, whether or not we're doing this problem or not, we need to make sure it's solved for y, so we can have that simply and ready to go. So how do we solve for y? Hopefully you recall that to get y by itself, you'll need to move anything that is around the y, and we have a certain order for that. We reverse PEMDAS when we solve. So if we're solving for this y, we will get rid of any subtraction addition first, doing its opposite operation. That would be, instead of subtracting 2, we add 2. And the second thing we do is we get rid of anything that's being divided or multiplied to the variable that we're solving for. I'm going to update my problem. So on the left side, we have x plus 2, and that equals 3y on the right side because the 2 and the negative 2 have vanished. We did his opposite operation to make that go away. So now we're at the point where we get to divide by the 3. So all of that, everything on the other side is going to get divided by 3. The 3's cross-reduce out, and that makes them just have to be a 1, equivalent to a 1. So we've got 1y, and that equals, now here's your thing, here's the deal. You can leave that y on the left-hand side or the right-hand side, doesn't matter. You can put x plus 2 all over 3 as it's written right here. Or you can go ahead and tell me x is divided by 3 and 2 is divided by 3. This is the same thing. I just broke those apart. The numerator, both terms, x and 2, are being divided by 3. And if you really want to get fancy, especially because I'm going to be asking you to write it in function notation, you can tell me f to the negative 1 of x, because that tells me you just found the inverse. And the inverse equals, the inverse is, well, x divided by 3, there is 1x right there. So technically, that is 1/3 of x. 1x divided by 3. And then your 2/3. Now, what's crazy cool about all of this is that any of these are acceptable because they're all the same. They're all equivalent. No one's going to scoff at any one of those options. Okay, let's try another one. Example 2. Now, this is telling me to find the inverse. I probably should have the word find written above it. So find the inverse. I know it's telling me to use the f of x function because of this f right here. It's also the only one that I have is f of x. But if it said g to the negative 1, g to the negative 1 of x, then I would take whatever the g function is, and I would find its inverse. So, realizing that f of x is a fancy way to write y equals 1/2 x minus 8. Step 1, switch x and y. So, x equals 1/2 y minus 8. Forgive all the color changes, but I want you to see that I'm literally just swapping only the x and the y's locations. Okay. To solve is to reverse PEMDAS, reverse the order of operations, by using inverse operations. So we're going to get rid of any subtraction or addition that's happening to the variable that we want to solve. So we want to solve for y. So I'm going to be getting rid of the minus 8 and the multiplying by 1/2. So I'm going to start by adding 8 to both sides of the equal sign. I'm going to go ahead and update my problem. X plus 8 equals 1/2 y. Now I'm going to get rid of any multiplication or division that's happening to that y. So y is being multiplied by 1/2. Before you do this, before you divide by 1/2, mathematically nothing is wrong with dividing by 1/2. The problem is mentally. Mentally, that is really, really tough to understand for anybody. So x plus 8 divided by 1/2, whoa, too much, too much. A long time ago, you learned somewhere in your schooling that to divide by a fraction is the same thing as multiplying by its reciprocal. So if dividing by a fraction could be done differently, and by differently I mean multiplying by its reciprocal, instead of dividing by 1/2, why don't we multiply by 2? Now, if that confuses you, let me say it in a different way. If I take this 1/2 y, I'm going to move it and give it some space. I see that I have y being multiplied by 1/2. What could get that 1/2 to vanish? The reciprocal of 1/2 is 2, 2 over 1. If I take 1/2 and 2 and multiply them together, 2 times 1/2, 2 halves. Well, that makes 1 whole. So I end up with 1 whole y. You can see that the 2's are going to cross out, and you're going to end up with 1 over 1 anyway. So understanding this, if the division of a fraction makes you crazy, because it does for a lot of people, then don't do it that way. What's going to get rid of multiplying by 1/2? Multiplying by its reciprocal. So I'm going to multiply by its reciprocal, which is 2, 2 over 1. But remember, what I do to one side, I have to keep balanced with the other. So I'm going to multiply also by 2 over 1, which is the same thing as 2, on the other side. So in doing so, everything over here on the right-hand side, gone. We have 1 y left over because we got 1 over 1. That's all that's left. So that's done. On the right-hand side, on the left-hand side, I have the distributive property, 2 times x and 2 times 8. So 2x plus 16. So write in function notation. All that means is put a fancy f to the negative 1, and then tell me what you found. Y equals, or f to the negative 1 of x, forgive me, equals 2x plus 16. That is the inverse of that guy right there. Now what's really cool is if we actually were to graph both of those, they would end up looking just like that graph right there. I mean, not exactly, but the same concept. 2 lines reflected over the linear parent function. Beautiful, perfect matches. Okay, now the last piece. How do you prove 2 equations are inverses without just doing a whole bunch of switching x and y and solve for y in 2 different cases? You can do it that way, but there's got to be another way. So you just finished a lesson on composition of functions, where you put one equation into the other and simplify. Well, that's exactly what you do when you prove inverses. F of g and g of f, you're going to find both of them, and if they both reduce down to a simple x, I mean literally the cute little plain x's you see right there, then that is proof that your two equations are inverses. So, prove that f of x, 4x minus 2, and g of x, a fourth x minus 1/2, are inverses of each other. They may or may not be. You don't know until you actually do this process. Let's do it. Now, I'm going to keep color coding for clarity. I'm going to make f of x blue and g of x red. So, if I'm going to start proving that they're inverses, I need to find f of g of x. And since you just learned how to do this process, I'm going to refresh it, but not spend too much time on it. So, how do we find f of g of x? Well, let's start with f of x. Let's get it ready. F of x is 4x minus 2. Since we're finding f of g of x, remember what's inside the function goes into the one that's in the outside of the function. So we're going to put g of x, what g of x equals, 1/4 x minus 1/2, and we're going to substitute it in for every x we see. That's the space that I have left, right there. So where x is, I'm going to sub in 1/4 x minus 1/2. Okay, so a fourth x minus 1/2 has just been plugged in for x, and now we're going to simplify. If these two functions end up being inverses of each other, you should have a plain x left over when you simplify. So let's see if that happens. Now, just going through basic simplifying skills, I see a parentheses, I see I'm going to distribute that 4. So we're going to start with that. 4 times a fourth x, a fourth of 4 is 1. So 4 times a fourth x, a fourth of 4, ends up with 1x. We're already off to a really good start. Let's keep going. 4 times negative 1/2. Half of 4 is 2. So negative 1/2 of 4 is negative 2. So this is negative 2. Now, I'm going to continue on my problem because I have this blue negative 2 left over from the original function anyway. So let's see what happens. Will the negative 2 and the negative 2 cancel out? No. No, it won't. I end up with f of g of x simplifying to x minus 4. It needed to simplify to just plain x. So no, these two functions are not inverses. Since it didn't simplify to just x, I don't even have to bother finding g of f of x. Now my question for you is, what would it have been? What would it have needed to be to actually make this work? Well, let's check it out. If that was a positive 2, right there, then this would have been a positive 2. And this would have completely vanished. And you would have had just plain x. Awesome. But it wasn't. It wasn't a positive 2. So it didn't end up being inverses. And that's okay. Now, if it had have gone on and been just plain x, you still would have to go back and reverse it doing it the other way. Just for your benefit. I'm going to prove it the other way. Well, prove it the other way as in it's still not right. So, let's switch it up. Still not going to be inverses. Now, you do not have to go to this amount of trouble. I'm just taking you through this to make sure you see that if you have to do it the other way, and by other way I mean finding g of f of x, what that would look like. So we take the g function, which is 1/4 x minus 1/2. Since f of x is what's inside g, then we're going to take 4x minus 2 and plug it inside every x we see in the g function. So this is going to be 4x minus 2. Hopefully your instincts are kicking in and you see the distributive property. We end up with 1/4 of 4x again, 1/4 times 4, 1/4 of 4x. We've got 1x. 1/4 of 2 is 1/2. So 1/4 of negative 2 is negative 1/2. And then we have this extra negative 1/2. So when I simplify this function, those don't cancel out. Those don't zero out. I have a negative 1/2 and a negative 1/2. That's going to be, I almost put negative 1/4. It's going to be negative 1. I don't get there. It doesn't get what we need. It doesn't get just plain x. So again, this is showing that these graphs are not inverses. If that would have been a positive 1/2, you would have had positive 1/2, and you would have had just x. But it's not. So no inverses. Sorry, moving on. Okay, I'm going to take that away so there's not any confusion. Okay. So the other and last and final thing to do is, are these inverses functions graphically? Now, I want you to see something. It's actually supposed to make it really, really easy. It is actually really easy to spot whether or not a graph is its inverse, or is a function of its inverse. I'm saying that wrong. Whether or not a graph is a function, and even how to determine if its inverse is a function. In our first lesson, you learned how to quickly identify functions. So we've already seen that you need no repeating x's, and it passes, what was it called? The vertical line test. How to test for a graph to determine if it's a function, the vertical line test. Remember what that means. That means we take any function. Let's see. Let's do like a parabola. And if your function, if your graph only gets hit one time by a vertical line, then it passes the vertical line test, and it means that your graph is in fact a function. In this case, it's a parabola. It's a quadratic function. Now, what's really cool is how to test if the inverse is a function. So what's really cool about this is it's just the opposite. Remember, the whole thing about inverses is that you switch x and y. So I want you to notice something. We're going to discover it for ourselves first. We're going to take the graph that we just drew, the parent function for a parabola, a quadratic function, and we're going to see if its inverse is a function. So, knowing that I have y equals x squared, switch x and y, x equals y squared, solve for y. If I solve for y, I have y squared. So how do I get rid of squaring something? I square root something. Now you've got to keep things balanced. You got to do it to both sides. So when you force a square root, you should already know, but you may not remember, and that's okay, that you have to show plus or minus the square root of that answer. Let me give you an example off to the side. If I asked you to tell me what x is, well, what number squared gives me 9? Clearly, 3 squared gives me 9. But isn't it also true that negative 3 squared, negative 3 times itself, also yields positive 9? See, when you force the square root, there's not just one answer, there's two. And that's where plus or minus comes in. It's signifying that we have two different answers happening there. Okay? So, what do we got? The inverse function, let's write that in the appropriate notation, f to the negative 1 of x is plus and minus the square root of x. Let me make sure this makes sense. When you graph your original y equals f of x, y equals x squared, you have a parabola. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, negative 1 squared is positive 1, negative 2 squared is positive 4, negative 3 squared is positive 9. All I did was make a table. I picked x's, I plugged them in as inputs, they gave me outputs, there's my graph. Connecting the dots, of course. Now this is not going to be pretty because I'm not a great artist, but here we go. There is your parent function of a parabola. Do you see how it has two halves that are symmetrical? You've got the left half and the right half, and they're already spitting images of each other. That symmetry, when it reflects as an inverse, it also has to be present. That's actually why you would need two separate equations for your inverse. If you take y equals the square root of x, just as it is, a positive square root of x, you have the parent function of a square root. So 0 square rooted is 0, 1 square rooted is 1, 4 square rooted is 2, and 9 square rooted is 3. See, you only get half of the picture. That's not enough. We've got a full parabola. Where's the other half? So it's super important for you to realize that when you square root something, you need to show me plus or minus because there's another half to the picture. Now, how do you graph a negative square root? It's just the reflection. So you've got 0 square rooted is 0 times negative 1, still 0. 1 square rooted is 1. With the negative out in front, makes it negative 1. 4 square rooted is 2, but it's got to be a negative in front of it, so now that becomes negative 2. 9 square rooted is 3, but with 3 with a negative in front of it becomes negative 3. Here's the other half of the picture. Now we have, as you can plainly see, the correct inverse. Remember, no matter what, inverses, whether they're functions or not, they are still going to be reflections of their original graphs as reflected over the linear parent function y equals x. So here's y equals x. Now, just for confusion's sake, we have your original function, x squared. You have also the two functions it takes to make your inverse. So your inverse of the positive square root of x, and then this branch is the inverse from the negative square root of x. Here we go, wrapping it up. I went to a lot of trouble to figure out that my inverse does not pass the vertical line test, and therefore my inverse is not a function. It would have been really nice if there was an easier way to do that. I mean, I went through trouble of not only solving, I had to graph two separate branches and still had to then draw the vertical line test. So clearly its inverse is not a function. FYI, right in function notation, this is the winner for that, in case that wasn't clear. Plus or minus, of course, needing to be there. Okay? There's got to be an easier way. Welcome to math. There is an easier way, my friends. You could have just done a horizontal line test on your original function. If you already know your original function is going to be inverted, wouldn't a horizontal line test say, let's go super different. One right here. Wouldn't that act the same as a vertical line test whenever it's flipped? Yeah, the answer is yes. So, how do you test a graph to determine if its inverse is a function? Don't bother finding it. Don't bother graphing its inverse. Don't even bother graphing, all those extra points and connecting all those dots. It's easy peasy, y'all. Graph the original function. Draw a line through it and see if it hits it more than once. If your horizontal line gets hit more than once, then the inverse is so not going to be a function. It wouldn't pass the vertical line test. Now, what's one extra little tidbit? If this were a function, if it passed the vertical and the horizontal line test, functions, both inverses and originals, if they're both functions, they're called one-to-one. Let me give you an example. The cubic parent function looks like that. A vertical line is only going to hit it one time. A horizontal line is also going to only hit it one time. So when it passes the horizontal and the vertical, it is said to be one-to-one. It's a function whether you invert it or not. Okay, I hope this wasn't too terrible. I did my best. Have a great, great day.